Hey class, so we left off with the Basel problem, and we will pick up with that again. But first, I wanted to take a moment to talk about the storage of primitive data types in within memory. So as exciting as this sounds, it will feed into whenever we discuss the Collats theorem, the Collats problem. Um, so we'll come back to it here probably in about 10 or 15 minutes once we finish with the Basel problem. Um, but I wanted to discuss it first in terms of a single byte integer, and then in terms of a 4 byte integer, and then how ints and uh, longs and shorts and characters relate to their unsigned counterparts. So, what does it mean to have an unsigned integer? More importantly, what does it mean to have an unsigned character? Uh, so, um, so we'll discuss that, um, and then I want to discuss how floating point numbers and doubles are stored, and then I'd like to, if we have time, also discuss or introduce the concept of numerical integration. So we'll write our own sine function, we'll write our own cosine function, we'll write our own exponential function, uh, and uh, and then we'll understand, hopefully after our discussion of how we're storing the data, and then in terms of how these integrators work, where error gets introduced, precision, error just as a limitation of the precision of how we store the number. Okay, so we begin this discussion with integers, and then how, and then we'll carry on from there. Okay, so an 8-byte integer. Uh, let's start by thinking what it's like to have an 8-digit number in base 10. Right? So, okay, and then in the United States, we will typically add commas. In other parts of the world, they'll use periods, and then the radix point will be separated by a comma. Right. So this is a cultural thing that you're going to have to watch out for if you ever end up coding uh, for anyone outside of the United States, any English-speaking nation outside the United States, or other countries. So some nations use periods just as their notation that the number has carried on, and the radix point is marked with a comma. But here, our local custom, and let's try and go with the local custom, is to use the commas as the separator and the period as the decimal point. Okay, so this is an 8-byte integer. We can imagine that there's zero remainder or zero fractional portion, so we can explicitly state that. And so, this is already so intuitive for us. So we look at this and say it's 87 million and something else. But let's slow down and explicitly state what it is that we claim whenever we write such a number in decimal. So we have one number, a 1 in the ones place. A 2 in the tens place. A 3 in the 100s place. 4 a 4 in the 10,000 or in the thousands, 5 in 10,000s, 6 in the 100,000s, 7 in the millions, and 8 in the 10 millions. And so, we learn just along the way various representations for this. And whenever we learn scientific notation, one of the things we learn is to represent it as a single whole number followed by some significant number of digits after the decimal place, and then we multiply it by an exponential form. So this is exactly so we slide everything over 7 places, right? So this is 8.7654321 times 10 to the 7, right? Or it's approximately some cutoff of that, 8.765 times 10 to the 7. So it's still the same exponential value that we use whenever we expand it out. But whenever we have it in this notation, an exponential notation, or scientific notation, then we tend to shorten it to some number of significant digits. Okay, so this is what it looks like to the left of the decimal. Can we apply this rule to the right of the decimal? Well, sure. I mean, we kind of already see it. So and I won't go as far this time, right? So we still have the 10 to the 0 place just to the left of the decimal. Then we have the tenths place. So that's 10 to the minus 1. The 100th place. The thousandths and the 10,000ths places. And so the trend holds where each exponential power of 10, which is our base number system, and if you remember, I think it was exam 1 had the polynomial on it, where we considered numbers, writing numbers in any base system as coefficients to a power series that looks like this. Or this for fractional values. And so we can write, or we do write all of our decimal values using this system. And we just do it so effortlessly that we never really give any thought explicitly to what we're doing. But our choice of 10 digits is, I believe it to be based on the fact that we have 10 fingers on our hands. Some cultures favored a 12 number base 12 system. Computers tend to favor either binary or octal or hexadecimal. So 2, 8, or 16 is your base number. So it can really be applied to any integer base number. I suppose it might be possible to do it with a fractional one, but if you did it, then you would be inventing something new. So make sure you document your research if you insist on trying that. Okay. So then, in theory, we could just swap out the base for whatever we wanted. We could change this to base 8 if we wanted. right? And then all of the rules still hold. This is a very different number, though, because we're in a different base system. And this one isn't even valid. That's like having a 10 in decimal, right? So you can have the value 10, but you can't have a 10 in the tens place. 10 tens is 100, right? We call it something different. So those conventions where you can't have your base number in any one of the slots. It ranges from 0 to b minus 1, right? So from 0 to 7 when dealing with octal, 0 to 15 when dealing with hex. You still get 16 numbers in hex. It's just that one of them is 0, right? So 0 counts as one of the numbers that you can represent. Okay, so then we can do this in binary, right? We just keep track. All we need to know is whether we're dealing with numbers to the left of the decimal or to the right of the decimal. So for integers, we know we're only dealing with numbers to the left. Okay, so this is our base, right? And we're going to fill in the slots with some number. And it's all ones and zeros. Okay, so if we add it up like this, right, we have 8 bits, so 8 binary digits represented. Then we can convert it to decimal by taking advantage of the polynomial, right? So the polynomial converts everything back to base 10 for us. So right. So we have it here in powers of 2. We can convert these to decimal and then add them all up if we wanted to get the equivalent value. So 2 to the 7 is 128. 2 to the 6 is 64. 2 to the 4 is 16. Squared is 4. And then 2 to the 0 is 1. So when we add these up, we get 85, 80, 208, 213. Okay. So that's our decimal representation. That's great. How do we represent fractions? How do we represent negative numbers? So let's talk about negative numbers, and then we'll talk about 4 bytes and 8 byte integers, and that discussion will be quick relative to this part. And then we'll talk about fractional values and stuff like that. So how single floating point precision arithmetic works and double floating point precision works. And that's just 4 byte decimal numbers and 8 byte decimal numbers, right? Using the IEEE standard for floating point numbers. Okay. So negative numbers, well, if you want a single byte to represent both positive and negative numbers, you have to account for the sign. So what is the sign? So you change one of these bits, right? Instead of representing a number, it now represents the sign. So it's positive whenever the sign bit is 0, and then it's flipped whenever it's 1, so that it's negative whenever it's 1. And so we can think of this now, instead of where previously it was 2 to the 7, now it's the sign is equal to negative 2 to the 7th, right? So why, when we just want to multiply by negative 1, do we represent it as adding negative 128 for a single byte? Okay, let's take a moment to explain that. It's called 2's complement arithmetic, and so it's how we represent negative numbers using 1, 2, 4, and 8 bytes, or arbitrarily long. We use 2's complement arithmetic, and it works like this. So now this signed character, this signed byte, has 2 to the 7, so that becomes negative 128. And then this becomes 85, 43, negative 43. So these are drastically different numbers based on whether we're considering it as an unsigned byte or a signed byte. And so essentially there's no other way to represent integers. I mean, you might be able to do it without 2's complement. You might be able to do it. You could do it where you have a sign where you always count up from 0, right? So 1's complement is where you have 2 zeros. You have positive 0 and negative 0. And this bit, instead of adding the most significant bit as a negative number, as beginning as far back away as you can, you instead start at 0, so that here you have positive 0 and negative 0. But it's wasteful, right? You don't need 2 representations of 0. You could either have one more positive number or one more negative number. But because this is one of the 2 to the 7 possibilities, right? It from 0 to 127. That extra number, by the way we've defined our arithmetic in 2's complement, and remember this is 1's complement, where just the sign bit and then everything after it, if it was 0, it's negative 0. But if it's 2's complement, then this is negative 128. And it's just to gain one extra number, but it's not just to gain one extra number. This method has the added benefit that if you add 1 to this, you get negative 127, which is what you get when you add 1 to negative 128 in general, right? So the arithmetic continues to be consistent whether you're dealing with positive or negative numbers. So you can use all of the same logic gates, all of the same architecture within your processor to do arithmetic between positive and negative numbers. So 2's complement, it gains you that extra number, that one extra number, but more than that, it preserves all of your arithmetic. And so then the only trick at that point is figuring out whenever you do multiply by -1, when you go from positive to negative, uh, how you um, adapt your number, how you flip all of the bits, right? And so in one's complement, whenever you flip the bits, you're really just flipping this one bit, so it's pretty easy. But whenever you do it in two's complement, you flip every bit and then you add one, and that's in both directions. So it seems a little odd, but the operation cancels itself out so it's periodic every two times it's applied. Okay, so this rule of the most significant bit, that's not unique to just a byte, right? That holds with 4 bytes. So with 4 bytes, then 2 to the 31, right? If it's a signed integer, a signed 4-byte integer, then the signed bit carries the value of -2 to the 31, which is something like 2.14 billion or something. Anyway, so that's 2's complement, right? The motivation behind it, the ways to think about it in terms of the expansion, and how it applies to integers of any number of bytes. And so it's really convenient, in particular because it preserves the arithmetic of adding and subtracting integers. It's perfectly compatible with the unsigned representation, or the positive representation of those integer values. Okay, so that's the spirit of what we're doing whenever we're representing integers, right? So then how do we all of a sudden switch over and represent floating point arithmetic, or decimal or fractional arithmetic? How do we add those numbers together? And the answer is series expansions. For Okay, so you'll remember how just a moment ago, or a few moments ago, we had our scientific notation. 9.87 times 10 to the 8, right, and then expand it out. So we're going to try and do something similar with our floating point arithmetic. And so subtle in this is something that might not be so obvious, but we're going to take advantage of the fact that this allows you to slide this decimal point, the mantissa or the radix point, wherever you want, right? So that the number 132.5 I want to slide it 2 to the right, so that it really blends everything in the scientific notation. It blends all of the numbers together into just this single representation. And so we would like some way to store that, hopefully in 4 bytes or 8 bytes if we are dealing with such advanced machinery as we are 50 years on from the release of Unix. Okay, so then how do we do this? Well, we need to store the sign, right? So let's limit ourselves to 4 bytes. So 4 bytes. Is 32 bits. So we have a constraint. So given this constraint, what can we do? Well, we want to store positive and negative numbers, and we've already seen that requires a sign unassigned bit. So we will we'll just deal with that. So our first bit, our most significant bit, is now set aside for representing positive and negative. And then we have the digits that, really we just have all of all of the numbers combined. We could move them. We could move this wherever we want, but the key is really in representing these numbers as just a single number, and then taking the exponent over here. So instead of dealing with powers of 10, since we're storing it in binary, we should deal with powers of 2. Right? So we have this part. It's almost certainly not what it's properly called. Okay. No. I don't remember what the name is for that part. And then we have the exponential number here. And then we don't need to store the 10 or the 2 because we're designing this. We can specify that it is always 10 or it is always 2, or whatever the most desirable value for us in creating this standard is. So then we need this. Okay, so in numbers that humans deal with, we tend to favor numbers close to 0, and exponents grow really fast. So most of the time, we're either going to want a bunch of numbers between 0 and 1, or a bunch of numbers between 0 and between plus or minus, I don't know, like 4 million, something like that. And that satisfies us. We don't really need a whole lot more than that. So we don't need all that many of our 32 bits, our tiny allotment of storage space, to go into this exponent, which is going to create just this astronomically large number, or this infinitesimally small number that we really have no practical use for. So most of our concern should be here in representing the number of significant bits of our scientific notation. And the exponent, it just needs enough to get by. But if we want to represent fractional values, right, we need to be able to move the decimal to the left or to the right, or our radix point, or our mantissa, whatever you want to call it. Okay? So that needs to be able to move around. It needs to be able to float around, if you will. So the exponent can do that if it's allowed to be both positive and negative. So then what's the right amount of care to give this number? And the number that they settled on for floating point numbers, for single precision floating point numbers, is 8. Okay? So it's just like a signed byte, just like the numbers we were just looking at. So it can be positive and negative, and it's got 8 bits of precision. And then, well, we've used 9 bits. We used 1 for our sine. We used 1 for the exponent. Right? And remember, these can independently indicate negative separately, right? So we can have negative 1/2, right? That's a perfectly valid value, which would mean that our sine would be negative because it's a negative number. And then the byte that represents this exponent value would also be negative because it's a value that is smaller than 1. Okay, so and then so we've used 9 of our 32, which means the other 23 are going to live here. Okay, so 23 bits, 8 bits, and 1. And so you won't be tested on that in my class, but you need to understand that this is what we're trying to do whenever we deal with floating point numbers. And the pigeonhole principle should tell you that even though we can represent these really large numbers by taking advantage of the exponent, we're still limited in the number of distinct values that we can represent with 4 bytes or with 8 bytes by the pigeonhole principle. So the number of values that we can distinctly represent are in one-to-one correspondence with the 2 to the 32 or 2 to the 64 distinct possible representations here. Right? So that's how many distinct numbers we can represent. But the range is much, much larger because we allow this to vary. Okay? And so this is the case for single precision floating point numbers. A double, which is 8 bytes instead of 4 bytes, uses similar logic, but instead of 1, 8, and 23, right, we have 8 bytes that we can work with. Or 64 bits. And for that, we use 1, 11 bits for the exponent. Right, so this is now represented by an 11-bit number. Or and 52 bits for the precision. So you can double precision numbers tend to work pretty well. You can do what you need to with them. And so if you find yourself in a case where you need to represent something that's smaller, or you just need the logic, the arithmetic of one of these, of something like a floating point number, and you have to create your own, well, understanding this will go a long way in helping you. But I can tell you that the hardware that does the arithmetic is optimized for dealing with either 32-bit words or 64-bit words, depending on what your processor is. If you have a 64-bit machine, then it'll handle 32-bit fine, and 64-bit because that is what it was designed to do. But larger, custom floating point numbers are going to require more computation and probably more memory. But if it's what you need, you can create it for yourself with this understanding of how it was done before. Okay, so it took a bit longer to discuss that, but I find it helpful in understanding where error starts to creep in terms of our ability to measure, and why whenever we test for equality with floating point numbers, we don't always get exactly what we want. Sometimes there's this little bit of error, and it comes in because as you're converting, like the number 1/3 cannot be exactly represented using a binary representation. It can't be exactly represented with 8 bits. Can't be, or with 4 bits, or sorry, 4 bytes. Can't be done with 8 bytes. Can't be done with 1,000,000 bytes. Right? It just always has this carryover. It's like the repeating decimal, so 0.3333 whatever, and we put the bar over it to indicate that you have to continue to add 3 forever to get 1/3 exactly right. And it's the same case whenever we try and represent it in binary. And so what happens is we truncate that sequence, so we don't have the way of writing the bar over, and we just round it up and we say, okay, well, just continue to compute 1/3 as far as you can, and then round up the last bit, and we'll call it even. Or if the carryover bit is 0, then we round down. If it's the first truncated bit, if it's 0, we round down. If it's 1, then we round up. It's like whenever you get to 5, round up if it's 5 or greater, and down if it's less than 5. Okay, so back to the Basel problem. Okay, so we wanted to know what the solution to the infinite sum 1 plus 1/2 squared plus 1/3 squared plus 1/4 squared, and so on, over all of the positive integers. So we're told that it equals pi squared over 6, and we want to know why. So let's get back to that. Okay, so we looked at the series expansions, and then we also said that there was a factorization where we could treat it like a polynomial, and we have this idea that really anything could be represented as a product of its zeros if you considered it as a complex valued polynomial, and that was exactly what Euler thought. So before it had been formalized that you could do such a thing, he poked around and saw whether or not it led him to an answer that agreed with what he already understood. So he had the series expansion. And we know, just by virtue of when we're born, that there is no quadratic equation, or like there is for the cubics or the quartics, for quintics and higher. Right? So if you have a polynomial that has something that's x to the 5 or x to the 7 or higher, there's no formula that we can just plug in and get the roots to the equation, the points where y is 0, the values of x where y is 0. And so if you have an infinite polynomial, well, there's no chance. You have no chance possible of getting some general form. And I think Euler knew that, and he had this aha moment where it's like, but I already know where it's 0, because I know where sine of x is 0. Sine of x is 0 whenever x is 0, or whenever it's some other positive or negative multiple of pi. So he jumped to that conclusion. He factored the polynomial using known zeros. He said, all right, well, if I just start there, maybe I can find some way to make these two meet in a satisfactory manner. So this represents that the equation should be 0 whenever x is 0. This factor represents that it should be 0 whenever x is equal to pi. this one whenever x is equal to negative pi, and so on and so forth. And then he paired them up based on just the integer multiple of pi that x is 0 at. So here, plus and minus pi got paired up, plus and minus 2 pi got paired up, plus and minus 3 pi. And because of that, it was convenient to write it in even shorter format. So the product of this, right, the product of 1 minus a times 1 plus a is going to be 1 minus a squared. So if this is a, and if this is minus a and this is plus a, and when we multiply them together, it's 1 minus a squared. Right? And so that holds for each of these integer multiples of pi. So that it's x times 1 minus x squared over pi squared times 1 minus x squared over 2 pi squared. So this is just another way of representing sine of x. But now we're doing it as this infinite product, and you'll note that Euler was one of the pioneers of exploring infinite products. So we already had infinite series, and we were curious when you could add an infinite collection of non-zero terms together and get something finite, or get something that tends towards something finite. And Euler was really one of the first to ask whether you could do the same thing with multiplication. Could you multiply an infinite number of factors which are themselves not equal to 1, right? Not the multiplicative identity, just as for summations we considered something that wasn't the additive identity. Could you multiply these terms together and get something that is finite? And the answer is yes, under certain circumstances. And part of that is understanding the way that you can relate these back to infinite summations, which were a little more well understood. But anyway, problem at hand, right? The Basel problem. So now we have this collection, right, where it's going to be 0 at plus or minus the integer multiples of pi. So these terms, these factors all look good, but there's this x that's sitting out in front as well. And so he did two more things, and that sort of allowed him to get close enough to see that this indeed was the answer. So the first thing that he did was he divided both sides by x to get rid of this leading term over here. So divide by x over here. And then over here, it removes a factor of x. Right? So for these, the x is already sitting out front. So to remove it, we just erase it. But for these, you have to factor it out of, it's the distributive property in reverse, right? So a times, in parentheses, b plus c is equal to a times b plus a times c, right? If you distribute. And so going in the reverse, if you have a times b plus a times c, then to factor it out of all of the summands, so you have a times, in parentheses, b plus c. Right? So that's what we're doing here. So we want it x times 1 minus x squared over 3 factorial plus x to the 4 over 5 factorial minus x to the 6 over 7 factorial. And so on and so forth, all the rest of the way. Right? So we factored it out. So each x term loses a 1 in its exponent. So this becomes a 1. Okay, so so it's looking a little bit better, and we can kind of see that, well, over here 3 factorial, that's 6, and there's a pi squared over here, but I'm not exactly sure where to go from here. And this I think was the it was a really clever solution just in general, right? But I think probably the boldest step here was to take this infinite product, right, this product of infinite terms, and multiply it out. Right? So he knew that he could construct this because he knew where this function was 0. And he also knew that we treated it as a polynomial, so it should obey these rules. And he realized that he didn't need a whole lot more than he already had. All he needed was a couple of multiplications. And so if you remember, whenever we multiply two values that are in parentheses, right? So two binomials. A plus B times C plus D, right? We multiply the first so FOIL, first the outer, so A times C plus A times D. The inner, so B times C. And then the last, so B times D. Okay, and then that rule holds whenever you have a third binomial that you consider as a factor. And so you tend to just pair them up, and then you expand it to this point, and then you apply those same FOIL rules to whatever the next parenthetical factor is. So here we have this infinite collection. So are we going to be able to do this? And the answer is yes, to a point, right? So for this first one, okay, he knew that if you multiplied, like, if you applied the first rule, right, first, outer, inner, last, well, the first rule, so A times C, is going to create this, right, this AC term, and that's always going to be 1, right? And so if you take the first from every one of these factors, well, it's 1 in every case. So he knows that that first term is 1. Well, that exactly matches the one that we have over here. Right? And then there's no x to the 1 term here. These are all x squared, so you're only going to get even powers of x. And so he realized that you could group like terms. Like if you could multiply out enough of this to get some traction, then you could group all of the x squared terms into a single coefficient, right? And then you could compare the two because we group like terms, right? So the x to the 0 value over here should match that, and it holds. The x squared coefficients will equal each other, the x to the 4, and so on. But he really only needs to do one more. And so the x squared terms are the ones where you do all first terms, right? You take the 1 from every single one except 1, and it's every combination of that, right? And so what do I mean by that? So here we're going to take the second value in our binomial, right? And then we're going to multiply it by 1 from every other factor. So that's negative x squared over pi squared. And then we're going to take the 1 here, and then we'll take the second one here, and then we'll take the first value from every other factor, so that we end up with this, right? As we're multiplying it out, we now have this value. So we've added negative x squared over 2 squared pi squared. And then we would do the same thing with the third. So we always select it just once in order to get that x squared term. And if we wanted the x to the 4, then we would take these pairwise. We would take them 2 at a time, which is so much nastier, right? But we only need this first one, right? That's all we really care about right now. So so for these, then we would have added also negative x squared over 3 squared pi squared, and negative x squared over 4 squared pi squared, and negative x squared over 5 squared pi squared, and so on for all of the integers. Right? So we want to group like terms, so we need to factor out the x squared. So then this becomes negative x squared, right? Because all of these are negative, so we can factor that out too. Times 1 over pi squared plus 1 over 2 squared pi squared plus 1 over 3 squared pi squared, and so forth. Right? And so now we can equate them. Okay, so first we have this one, right? That negative x squared over 3 factorial. Should equal this, right? This negative x squared So we have negative x squared over here times 1 over pi squared plus 1 over 2 squared pi squared, and so forth. Sorry, I know it's a little blurry, but if you've been following along, you should know what it is. Okay, well, we have x squared on both sides, so we can just cancel that. We really only used it to compare the coefficients. Right? So that goes away. Comes a 1. So over here we have 1 over 3 factorial, or 1 over 6. And over here we have, well, really we could simplify this if we pulled pi squared out, right? If we just factor that out. So we have this 1 over pi squared, and now we have one over pi squared times 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. Well, I mean, that was exactly the sequence we were considering. So if we just move this term, if we multiply both sides by pi squared, then we know what this adds up to, right? And it's pi squared over 3 factorial is equal to that sum of the reciprocal squared that we were first considering. And so it's a nifty result. It's super cool, but I want you to take it in context that it took one of the most brilliant mathematicians in history years of just diligently adding, 1 decimal place every like 11 months or whatever to this result that he had, until finally he had the key insight that allowed him to get this much cleaner result. So don't get too discouraged if at first you don't see the solution, or if it feels like that as far as you can see all that's left is just having to grind out and work really hard for these not terribly satisfying results. So you put the work in first, and then eventually the payoff will be there. But it takes a bit of time and patience to get there. Okay, so we can begin discussing the Collats theorem, but I think I'll just introduce the problem to you, and we can go over how to treat it on Tuesday, and then we'll spend the rest of the time tinkering with creating our own sine and cosine and exponential functions and discussing numerical integration and so forth. Okay, so for this one, it's a recursive function, so it fits in nicely to our course. But it's a recursive function that has conditions to it. So you do a different behavior if the function is even, or if the value of the previous term is even, or if it's odd. So the next term in the sequence is going to equal to half of the previous term if the previous term was even, right? So if it's even, shift right. And if it's odd, then multiply it by 3 and then add 1. So this will give you an even number on the next term, right? Because any odd number times 3 is going to again be odd. And then when you add 1, well, an odd number plus 1 is going to be an even number. So, okay, we'll discuss sort of how to look at this problem in the light of everything that we've learned in terms of binary representations, and then we'll get to discuss trees and decisions and so forth whenever we approach it. But for now, let's play around with numerical integration. Okay, so sorry. Okay. So the first thing I want to do is create the sine function. Right? So there's already a built-in one. It's 0 at 0. It's 1 at math.pi divided by 2. It's square root of 2 over 2 at math.pi over 4. And it's negative 1 at 3 pi over 2. And so remarkably, the series expansion gives these values. And so we can create our own. So let's create, so I don't believe there's a sine defined. Right, excellent. So we can create our own function. And it takes argument. I'll shorten it to arg. Or you can call it angle if you want. And we're going to treat it as a sum because that's what the series expansions are. Right? So it's a sum, and anytime you start with a sum, you want to initialize it to 0 because you're going to be adding values to it. And then we're going to have to make some decisions in terms of how far we want to go with our arithmetic. But we'll just cut it off after a reasonable amount. So we need an iterator, right? Some index variable, and this will this would be the subscript in terms of the terms of the sequence that we're adding together. And we'll do 10 loops. We can do, or 10 iterations. We can do more if we care to. So we could define some default variable that says iterations max or whatever. We can do that here. So we give our chance to increase the precision if we can, or if we want to toy with it. But if you remember from when we were discussing floating point numbers, there's going to be a limit to how precise we can make our number. And then adding additional terms to it, it's going to hover, it's going to fluctuate around the actual summation. So you don't want to go too much further past whatever that optimal point is. You don't want to go any further past whatever that optimal point is. Okay, so we know that we're looping, but then what are we adding together? Okay, so if you recall, sine of x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so forth. Right? Well, okay. Okay. So our sum is going to be this. We're going to add term by term. So we know that x is going to be our angle, right? So it's angle, and it's going to be raised to whatever this power is. So if we're starting at 0, then here it's 0 plus 1, and here this would be I equals 1, and 3 is 2 times 1 plus 1, and 5, well, this is the term I equals 2, and 5 is 2 times 2 plus 1, and 7 is term 3, I equals 3, and 7 is 2 times 3 plus 1. So it looks like we found our pattern. And so it's going to be twice I, so 2 times I plus 1, and that's going to be our exponent. Okay. Well, the exponent matches this factorial over here. So we need, on the bottom, we need factorial of that same number, 2 times I plus 1. But we haven't defined the factorial function, and so we can actually define that here. We can create this constant factorial function, which takes some value n, and then we have a product. And so we always initialize them to the identity. When we're adding, when we do a summation, we initialize it to the additive identity. When we're creating a product, when we multiply, we do it to the multiplicative identity. So then, while, let's see, if n is less than or equal to 1, just return 1. Otherwise, while n is greater than 1, we want to multiply. So whatever our current product is times that. But then we want to decrement it afterwards. So we can do this in 2 steps, right? Because there's always another way. Right? So we can multiply our product times n, and then we can decrement n, where we can do it in a single line if we're comfortable with this syntax. But we can do it in 2 lines to make it a little bit clearer what we're doing. Okay? So we continue to multiply by n, and then we decrease. So if n is 3, then our product starts out as 1. We skip this. We enter our loop. We multiply 3 times 1, and then it gets decreased down to 2. And we multiply 2 times, well, this is now 3. Right? So 2 times 3 is 6. And then we decrement, and it's 1. And so we exit the loop, and then we return our product. So we now have a factorial function, which is great because we're going to use it right here. And then we create our sum from that. And then once we've reached our maximum number of terms, our max iterations, then we exit the loop and we return that value. So now we return sum. Okay. So now the sine of math.pi. Oh, I guess we need more terms. Let's do 20. Oh, you know what? We haven't alternated our sign. Right? Okay, so we need to define sine, or we need to modify it so that let's start off with the sign, the signature, the positive or negativeness of the number as being 1. Well, and then we'll just update it each time. So sine is positive whenever I is 0, 2, 4, whatever, and it's negative whenever I is 1, 3, 5. So all of the even terms, if I mod 2 is equal to 0, then it's positive. And when it's on, then it's negative. So now we have this sign, and we'll just add that to the term, right? So now we have a positive 1 times x, negative 1 times x cubed, positive 1 times x to the 5, negative 1 times x to the 7. Okay, so let's see if that solved our problem. Okay, so it's negative 5, which doesn't look good. And then you look over here and you see that it's times 10 to the minus 10. So the error is just very minuscule. And we could try and add precision, and we see that the error now is on the order of 10 to the minus 16. So it's getting really close to 0, but because of precision limitations and the fact that it's an infinite series, we will never be able to get it exactly down to 0. But we can compare the values of our custom sine function. Compare. So we take an angle, and then we return sine of the angle minus the built-in of the angle. And then we could do an absolute value if we cared. So then let's compare at math.pi over 4. And the values are exactly the same at that angle. At math.pi over 2, at pi over 3, we see that we get a little bit of precision difference. But our sine function is doing the same thing that the built-in function is doing. So cosine is similar, but you use the series expansion for cosine, and then the exponential function would be similar as well. We can do the exponential function. I'll let you think about how to do the cosine function. So x, I don't think that's defined. Okay, so we can define our own exponential function. This takes an exponent, and then it's going to be a lot of the same tricks. So if you want to begin with this, then you can copy the code. But I really think you should type it out because you're developing those habits. Right? But we could still look back on it. So we know we're going to deal with a summation. So we want to begin our sum with a value of 0, the additive identity. And then we know that we're going to need a factorial function. So let's go ahead and include that. And then that will be the same as before. So we begin with a product, which is the multiplicative identity. We add some short circuit tests. Right? So if they passed in a value that's less than or equal to 1, we'll just return 1. And so the factorial function, the gamma function, which is the abstraction of the factorial, or it is the analytic continuation of the factorial function to include both fractional inputs, so rational values, real values, and other complex inputs. So the gamma function, or the factorial function, is actually a little more, or quite a bit more complex than this. And we could create a numerical integrator, and we will, that will compute values from that, so we could get fractional values. But for what we're doing for these series expansions, the factorial is just going to deal with integers. And so this is good enough. This is really all we need to handle. And then this time we'll use the shorthand. So the product is going to be a running product, and then we're going to decrement n each time. And then we'll return that. Okay, and then again we loop to do our summation. I will again be our index. We can do iterations max again. I guess that's fine. It's a good convention because it's a default variable. So even if you don't feel like specifying it, it defaults to a value for you. But if you find that you have a lot of error, then you can go back and increase the number of terms to see if that'll improve it. Okay, so now we make note of what the series we're using is. So the exponent of x is equal to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial, x5 over 5 factorial, and so forth, right? So the sign of every term is positive, and then we march on like this. Okay, well, we start off with a value of 1 in our sum, so we can already break our rule, right? We can begin our iterations, we can begin our index at 1, and initialize this value to 1. Yeah, because we always begin there, so that's always the first term. So even if the exponent is 0, well, e to the 0 is 1, so that would be correct. So we're going to make that modification, and hopefully it's clear to you why we are doing that, or why we are allowed to do it. But you don't have to. You can continue to do it exactly the way we did with sine, and it would still be just as correct. But just for variety's sake, I want to show it to you. Okay, so now, again, we're doing a summation. We don't have to bother with the sine factor this time, because everything is positive. So we're just doing the summation, and it is the exponent raised to the I. Right? So here it's x to the 1, and then x squared, and so forth, divided by the factorial of I. Right? So the 2 factorial, 3 factorial, and so forth. Okay, and then we return the sum. Okay, so the exponent of 1, that should be, we have e, right? Yeah, that's e to the 1. So you can see how close our computation is to that one. And if we wanted more precision, then we can try for that. Let's see how much further we got. And again, we could write a comparison function that subtracts them and tells us the absolute value of the difference. But you can see that this is a perfectly valid way of creating these functions. So you don't have to rely on these built-in functions if you don't want to. Definitely use them if it's provided to you. But if you come across a function that doesn't have some built-in analog that's already included in the libraries of whatever language you're using, it is possible. So if you have the definition of your function, even if it's an integral, if it's a summation, if it's a product, you can define it for yourself, and it's going to be just as good as if it had been built into that library. So just one final comparison, we'll do e cubed. So that's the built-in, and that's the value that we computed. So, okay, so we will carry on with numerical integration. We'll talk about Collats next time, and then hopefully I'll have something else for you as well. All right, have a great weekend, and remember to check for homework on the chance that I do end up assigning the next homework this evening.